Okay, good afternoon.
Welcome to this webinar on the outcomes of the GloBE project. Very happy to have so many of you on the call this afternoon. Thank you very much for joining us. This is the first of two webinars that Chris and I will be doing covering the outcomes of the GloBE project. And they're split roughly between the first session today, which is on the measurement aspects of the project, and the second webinar on Thursday this week on modelling and accountancy. So using the measurements that we talk about today to try and figure out what models work and then how we should use those models to predict the performance of wind farms. If we can just introduce ourselves quickly. My name is Neil Adams. I work for the Carbon Trust. I have a couple of roles here. Probably my biggest day job is looking after the Offshore Wind Accelerator programme, which is a big collaborative R&D project, which I will tell you about in a little while. And I've also been looking after the GloBE project from a Carbon Trust point of view. Chris, would you like to introduce yourself as well?
Yeah, thank you, Neil. My name is Christopher Rodaway. I'm our lead scientist for the advanced numerics capabilities within RWE. I sit in our resource assessment team within engineering as the function, and I was the technical lead for GloBE all the way through since its inception.
Thank you. I'll be kind of topping and tailing today's session, and Chris will be doing the meat of it. He's very much the brains of this operation. Just to explain a little of the background, so the Offshore Wind Accelerator programme, which GloBE grew out of, is a very long-running joint industry programme, which currently involves 9 of the major utilities, who have a huge proportion of the offshore wind assets in Europe between them. It was set up back in 2008 with the aim of bringing down the cost of energy from offshore wind, and it's addressed all sorts of complex and interesting problems since then, and Blockage is one of those many projects. We have a core R&D program, funded by these 9 partners, and then we have these larger spin-off projects that we call discretionary projects, where we bring in external partners and in some cases public funding as well, and GloBE is one of those projects. And it came about really through a long development. If we can go back in time a little bit, so historically the way that we modelled wind farms was we assumed that any turbines that were in the free stream, so those upstream turbines, saw the free stream wind speed, i.e. the wind that would have been there if there wasn't a wind farm present. And then we looked downstream of those turbines and we applied wake effects to figure out what the impact on those downstream turbines would be. And we considered all of those aerodynamic losses, those turbine interaction losses, to be wake losses. And for small wind farms, that worked pretty well for a long time. Problem was, as wind farms got bigger and denser and the North Sea especially became a bit more crowded, we could see we were missing something. There was some good work put out by DNV back in 2018, I think it was, and then picked up by some of our partners, in particular Ørsted, back in 2019, saying that, basically we're missing something here. This is more complex than we thought it was. There was an increased acceptance that the wind slows down as it approaches a wind farm, and that these turbine interaction losses are actually a complex two-way interaction between the turbines and the atmosphere. There's more going on there than just wakes. We did some work within the Common R&D programme, within the OWA, to try to understand this. And we came to some interesting conclusions there. I guess most significantly, the conclusion that there's more to it than a reduction in power at the lead row. By following through what the physics of that blockage mechanism actually is, we would expect some of that to be compensated elsewhere. So it's maybe not as simple as just applying a loss. But fundamentally, there was a lot that we didn't understand, and we decided what we really needed was a comprehensive measurement campaign to try to let us understand these issues in more details. And that became GloBE. We really had 5 objectives in GloBE. And if I start from the right, so the kind of final objective, what we wanted to do was increase confidence in the energy yield predictions from large offshore wind farms. To do that, we had to develop a consensus within the industry as to what was going on with blockage, what the physical mechanisms are, how they can be modelled, how they can be accounted for. To do that, we had a number of hypotheses, so initial understandings of what was going on with blockage. And we needed a way of testing those hypotheses in a way that was agnostic to which one was ultimately going to be correct. So we needed to develop this large, complex, rich data set. And to do that, we needed a sophisticated and complex measurement campaign. And that measurement campaign is really the focus of today's discussion. So the requirements on that at a very high level were they had to be agnostic to the various hypotheses about the blockage effect. So we had to be able to discern which of those hypotheses were or were not true. We had to be capable of discerning a very small signal amidst what could have been potentially a pretty noisy and uncertain measurement process. And it had to be something that we could do in the real world. So yeah, it's all very well designing these things on paper. Ultimately, you've got to get some pretty sophisticated bits of kit offshore and turn that into a realizable measurement campaign and actually capture the data. And a lot of those practical challenges, again, we'll touch on today. And the solution which came to that was the campaign design which RWE put forward at their Helgoland cluster. This was not just complex from a technical point of view, it was also complex from an organisational point of view. We have a huge number of parties involved here, and we'll run through this in a bit more detail later on, acknowledging all the various partners who came on in various capacities. The programme itself involved almost all of the core OWA partners, plus several other organisations who chose to buy into the project, alongside a number of research organisations, equipment providers and others who came in a technical capacity and also in a funding capacity. RWE were at the core of all of this, so it's their wind farm, and Chris has really been the technical lead, the technical guru in this all the way through. But we have pulled in a huge amount of external expertise, so DTU, TNO, Fraunhofer, Fraser-Nash, a number of these external organisations have been really critical to getting us where we are. And we have an independent technical review group, and we'll talk much more about their role in Thursday afternoon's presentation on the modelling and accountancy aspects of the project. We also have links with two publicly funded projects, so the Crosswakes project in Germany and the Affable project in the Netherlands. And again, we're grateful to the public funders of those projects to allow us to kind of build on what they were already planning to do and increase the value of the GloBE project. And at that, I'll hand over to Chris to talk you through the more technical aspects of the measurement campaign.
Thank you very much for the introduction. So I'm going to be going through the technical elements here. And I thought I'd reintroduce a series of authors that have contributed a huge amount of effort over many years that this project's been running to get us to the point that it has been today. So I wanted to name them individually, and I'll acknowledge at the end as well. And just a quick note on questions. If you have any, there is a Q&A section which you can enter questions into as we go, and we'll try and pick as many of those up as we can at the end. So as we go through this section, I'm going to introduce different stages. So we'll start off with the introduction and the motivation, then we'll go on to the experimental design, the results and findings from on the measurement side. We'll go on to the modelling side on Thursday, and finally the conclusions leading into any questions at the end. But starting with the introduction and the motivation. As Neil has pointed out, we wanted to use our wind farm locations for the purposes of GloBE. The wind farm is located in the Deutsche Bucht in the North Sea, and the characteristics of the wind farm cluster are actually extremely appealing for conducting an experiment such as this. So firstly, the wind farm cluster has a high installed capacity, nearly 1 gigawatt, and it has a very flat leading edge with respect to the most common westerly wind direction. We have two different styles of layouts, the Ammerbank West gridded layout to the top, and then a second wind farm, Nordsee-Ost, to the south, and in between those, we have this, what we call the Kaskasi Gap. There is now a wind farm there. Kaskasi wind farm is now operational. But at the time it was not, and we wanted to leverage that gap for the purposes of GloBE. We're far away from any coastal effects and neighbouring wind farm locations as well. And both wind farms are 100% owned by RWE, which meant that logistically it was a lot more straightforward to get this measurement campaign done. In order to reach consensus at the end, Neil has already mentioned these hypotheses that we wanted to test. We set up 5 main hypotheses, and the first of these is that there is no blockage effect. And hypotheses are statements of fact that you want to test to be true or false. The second one, H1, which is represented in the top right-hand corner, is that the blockage effect results in a downwards bias in AEP only. H2 is that it results in an upwards and a downwards bias in AEP, which is indicative of a redistribution style effect. And we'll come on to the subtleties around the naming conventions of these things in the second session. And the fourth and fifth hypotheses, H3 and H4, are entirely around the interaction with the atmosphere, and specifically that the boundary layer height has a little or significant impact on the blockage effect extent. And we have these different approaches, the no GB, the decoupled approach, where you try and couple together the H0 and H1 in some sort of fashion where you want to correct for the blockage effects in the lead row style. And then we have these tightly and fully coupled approaches where all the physics is trying to be baked in one overall turbine interaction calculation. So why this particular wind farm location? I mentioned this Kaskasi gap, which is extremely useful in terms of the opportunity to leverage this Kaskasi gap. The Kaskasi gap captures, as we see from three models demonstrated here. The left is using Wind Modeler, which is a RANS computational fluid dynamics code. The center, we have our internal VV model, which is a coupled viscous and inviscid model, which tries to capture the blockage effect also. And the far right is the highest order model that we ran during GloBE through the cooperation with Crosswakes, which is an LES, large eddy simulation, computational fluid dynamics. And in each case, we can see this characteristic deceleration of flow from the west. These are all flow coming from the west in this case. And then an acceleration going through this gap along this transect. So they all had similar sorts of behaviors, and we wanted to see if we could observe this in any sort of measurement campaign, and we use this for the fundamentals of the design. So that takes me on to the experimental design. Again, here we see on the right-hand side the wind farm configuration. There are actually three wind farms here, but we concentrated, of course, on the ones that were owned by IWE, which is Ammerbank West and Nordsjøs. And we planned to capture 4 points over 3 separate measurement locations in order to observe wind speed gradients forming as a consequence of blockage. We would hope to see similar sorts of gradients that we saw in the modeling, and if not, then that's a red flag for the modeling. So these points would come about with the use of 6 scanning LiDARs operating in 3 dual Doppler pairs. Operating in dual Doppler pairs means you can resolve your U and V velocity components, so you get a wind speed measurement and also a wind direction. And it also offers the opportunity for the lowest uncertainty compared to other scanning strategies like a full scan, although not as low uncertainty as simply staring in one place for the whole time. So we operated in a step stair pattern, and we also needed to motion correct and debias, ensure the devices were leveled and time synchronize in order to get overall measurement uncertainty that was low enough so we could see the blockage effects in the noise of the data. We also had another wind cube, which is dedicated for this boundary layer height measurement and tool VAD profiles. We deployed a floating LiDAR system, courtesy of Fraunhofer EBIS, again with this cooperation agreement with GloBE, in 3 separate locations, which is a crucial part in understanding what the overall uncertainty is that we achieved during the campaign. The first location is the green triangle, which is a co-located point to one of the dual Doppler reconstructed locations. And then we moved it far upstream to be representative of an upstream reference. And then we co-located it finally at the third point in yellow, the yellow triangle, which is next to the Nordsjøs Met mast, which is located here. And as part of GloBE, we also refurbished that up to 16 Hertz sampling frequency from ultrasonics and equipped it with more atmospheric stability measurements and sea surface temperature measurements. So this, we believed, would give us the rich data set that we needed. If we look at all the scanning LiDAR devices actually in situ, we have the 2. We install webcams on all of their turbines in order to continuously monitor the devices if there are any issues. So this is the first pair located on Ammerbank West. The second pair located across Ammerbank West and Nordsjøs. And the third pair similarly across the 2 wind farms. And then lastly, the 7th LiDAR, which is located on Nordsjøs. That's permanently for scanning vertically. I talked about this floating LiDAR device, which is located in 3 separate positions. We have position A and position C here of the floating LiDAR actually on location. You can barely make it out there in the first image. So I'll go on to an uncertainty and bias section now, which is all about how we control for known sources of bias, such that what we are left with is as close to a simple measurement uncertainty repeatability. We try to break this down into multiple different sections, but ultimately, if we are trying to measure something that is within 1 to 4% of wind speed, we are getting close to the uncertainty of any measurement system. And so if there is anything layered on top of that that we are not controlling for, we'll ultimately get to a point where any measurement to try and observe blockage becomes meaningless. And if that is the case, we could start to accidentally misattribute measurement biases to a blockage effect, which we don't want to do. An example of this is shown in some modeling that we did. It's very similar to DTU's the other model, except it's kind of semi-coupled to a wake model. The impacts of things like decreasing wind shear from 0.15 down to 0.09. Higher uncertainty is red, lower uncertainty is blue. So we're getting a larger blue region, which is good. And finally, reducing a line of sight uncertainty from 1% down to 0.2%. And this has a substantial impact on our ability to measure and capture the blockage effect. So after all the work that we did, and once we reached the go, no-go point during the project, we decided to proceed with the measurements because we believe that we're in a position to debias the measurements enough to see the blockage effect. So what are those sources of bias? The first one is a pointing accuracy and earth curvature topic. So is the drone actually in space? The LiDAR beam's pointing in space where we think they're pointing. Hard targeting was not enough. I mean, we use a hard targeting method where we try and use the LiDARs to observe a solid structure and then map those out geometrically to ensure that the commanded azimuth and elevation is where it is actually in reality. But in addition, we wanted to use a drone because there are no turbines upstream in the directions that we wanted to try and measure. So we developed it from scratch with DTU, and it's a phenomenal piece of work that DTU did. It's a completely bespoke and new and novel method to try and do this using a drone. The second part is the dynamic tilt correction or motion compensation, because the turbine structure is not static. And it will, any small deviations in your beam, even small at tiny angles, less than 1 degree, will have a substantial difference, tens of meters at the farthest ranges in your LiDAR beam. We wanted to make sure that the 6 devices that were in these dual Doppler pairs do not have systematic biases between them. We weren't too interested in the absolute wind speed measurements, but rather the relative wind speed measurement between them and reducing that level of bias. And finally, if there are any residual spatial effects resulting from ambient flow gradients or from far field wind farm wake, and that we needed to correct out. So the first one of these is going to be the removal of the earth curvature and decorrelation of turbulence at the measurement level. So the earth obviously is not flat, and as a consequence, we needed to adjust this so we weren't accidentally measuring higher in Z, so altitude above sea level as a function of range, and you do start to see this creep in. If we did that, then we would be biasing the measurements with a higher wind speed than is actually in reality. So we corrected these points in Z at the measurement source level. So we adjusted the elevations downwards as a function of range during the step steering methods to remove this effect. We also wanted to decorrelate advection of turbulence going through the wind farm and through the Cascadi Gap. And to do this, we had to focus on a primary wind direction, which was westerly, and we marched the points going upwind with respect to a westerly wind direction. And with all the scanning points did this at the same time. But we did want to try and correlate as much as we could in Z for the shear-based tilt correction method that we developed later. And that was why we did the steps, stepping up in the points in Z relatively quickly and a couple of times for each scan period. The second one of these points I'll go into, first of all, is this inter-device line of sight wind speed. So the wind speed being measured along the length of the beam and any time-wise variations in that as well. So the purpose of this is to identify and remove any residual biases that might have existed that have come out of the factory, because each device is calibrated and is unique and has its own level of measurement uncertainty. We did this before the campaign and after the campaign. We can see on the left, this is at the DTU's Risu campus, and they measured next to a reference mast with an anemometer and an octasonic. And on the actual Heligoland Island up to the right-hand side, we used a mass structure as well for the purposes of the hard targeting to make sure the beams were aligned. And the elevations and ranges were all pretty much identical between the two tests. And what this revealed is that one of the LiDAR units on the left-hand side, the GloBE 1 LiDAR, had an offset which we needed to correct for before the measurement campaign took place. And during the measurement campaign, GloBE 1's offset increased quite noticeably, and GloBE 2 also had a bias that was introduced during the measurement campaign. And we went through a big exercise to try and identify if this was a slow change over time or if there was a sudden change that took place, which we needed to try and identify. One thing you would note here is that all of the beams on the x-axis of these graphs is a function of range, and because all the lines are essentially parallel, there is no bias as a function of elevation, so the beams are not misaligned in this case, is one of those confirmations. So what did we do? We consulted with Vaisala to determine what sort of key identifier we should be looking for in the data. And we identified the times when the offsets actually occurred during the measurement campaign, and because of the nature of the change, we're looking for a sudden change in CNR. That's the quality of the signal, your carrier noise ratio, or signal to noise ratio. We conducted a test using a piece of data before the event took place, and then after the event took place, and we implemented offsets from the day when the actual event, the change took place. So we were able to correct out these biases that were introduced during the measurement campaign. The motion compensation is the next section that I'll go into here, using the high frequency measurements sampling of in kilometers. So we knew in advance of actually deploying offshore with GloBE, this is going to be an issue. So we did a pre-campaign for 3 months as part of the feasibility study and no-go decision. And what we did is we installed an inclinometer, where you can see in the images on the right-hand side, that's across two turbines across both wind farms, at the intersection between the transition piece and the turbine tower, which is where the service platform is, which is where the LiDARs would be installed. The questions we had at the time were, what's the peak tilt that we could expect? Are there any significant differences between the dynamic response of each foundation, because they are different foundation types? And can we use the data set to actually inform what the correction and motion compensation method should be? As I say, we measured for 3 months, and you can see from the time series on the right-hand side, the pink data set is Amrum Bank, and the blue data set is Naughty-Ost, and we do get a different dynamic response, but that actually required some post-processing. And what the outcome of that work was is that the peak tilts, even though we initially thought it would be up to 0.3 of a degree was our initial guess on what the peak tilts might be from experience. Actually, in reality, having post-processed the data to remove noise and unwanted accelerations, the peak tilts were around 0.2 and even 0.1 in some cases. So this is good from our perspective because it allowed us to lower the uncertainty associated with this effect. And what we see here, we have some videos here, is a lovely piece of work done by DTU again, which is a trolley fabricated from scratch by DTU with an actuator on it, which is then used to drive a LiDAR dynamically and scan next to the Met mast, which you can see on the right-hand side, and compare that to a static LiDAR. And this was the basis for the shear correction motion compensation method that we put in place. So this is a really nice test as to how much bias or how successful that approach would be. So where were we? We had the three-month pre-campaign tilt measurements. Then we developed this method for doing the tilt correction. And then as a consequence of that, we deployed interferometers that you see at the bottom on the left-hand side, and also accelerometers and gyros in case we needed to monitor what the acceleration about a certain axis was as part of the filtering. And on the left-hand side, you see the two different foundation types. The left is Naughty-Ost using the jacket style foundation. And on the right is Amrum Bank using the monopile foundation. So what does the motion compensation actually look like in the data? We took a moving average of the inclinometer data to filter out any high frequency vibrations and leave what we understood to be true inclinations. Then we collected points around the measurement points. You can see here actually along these beam trajectories, there's a concentration of points towards the end, which is where the target measurement location was, so a high concentration of points around there. We'd loop in as many of those points as possible, do for a 10 minutes aggregate, then perform a tilt correction on those. On the left is the uncorrected, on the right is the actual correct, is the real corrected for a relatively short period. And you can see the level of dynamic motion that's even occurring within I think it's just an hour's 50 minutes or an hour's worth of data. Oh yeah, and please ignore the points at the bottom. These are reset backlash points. Then we get onto the hard targeting section. So the initial process for this was that the LiDAR devices were leveled at the DTU campus at Riesen in Denmark, and hard targets were used onshore to perform that leveling. We assumed then, because there was no alternative, so that leveling would remain true when moving offshore. There's a lot in that because the devices have to be transported, installed, and there's lots of things that go into that. So we knew that we had to use a lot of hard targeting to gain confidence in the leveling of the LiDAR devices. And we also used almost weekly turbine hard targets to test the drone-based hard targeting methods and see if there are any temporal changes, any drift or anything like that that took place during the measurement campaign. And what did that drone technique look like? We can see on the left-hand side, this is where the drone is. We had set a commanded angle for inputs for azimuth and elevation from the LiDAR device, and then fly the drone into the beam at the points. We then hit the beam with the LiDAR. We got a hard target result, and then we plotted those points. You do that in 2 or more different azimuths at 90 degrees to each other, and therefore you're able to resolve what the pitch and roll and elevation offsets of a LiDAR device are. And this is all done using an RTK station, which you can see just here is in absolute space and relative space to this real-time kinematic station, but also using geometric information to calculate the positions of the LiDAR devices and the drone all relative to each other. We then use the turbine surrounding. We could not do this in multiple azimuths because of objects in the way of the beam. So we could only, apart from one turbine, actually only do a single turbine hard target. But these were done routinely, not quite weekly, but routinely. And these data were also motion compensated. We're using the same 30-second average filter on the motion data, using a reference points that we wanted to track just above the railing where the LiDAR head would be over time across each turbine type. This is a really nice plot because we have on the left-hand side the turbine in the raw outputs from the LiDAR. Then the second plots, we have the very noisy data, the unfiltered motion compensated data, which is what happens if you don't apply some filtering to the inclinometer. Then the third plot is having cleaned up those data. Each of the points looks like they've become slightly irregular, which is good. That is where the beam should be in azimuth and elevation, not where it actually was. And we see that the whole image has actually moved downwards as a consequence of that particular motion during that capture. And the whole acquisition took about 30 minutes from top to bottom to top. What does this actually look like over time? How do we leverage these measurements? Well, we see a time series with key points here. We want to concentrate on the circle points and the triangle points. The vertical line is the day that the drone flights were conducted. That was at the end of the measurement campaign. And we are tracking towards that, and the closer to 0, the better in these plots. And we can see in each case that having applied the drone-based corrections for pitch roll and motor offsets, that actually we track closer towards 0, although there are slight changes over time. We can't work out what those changes are as a consequence of. It could be resulting from a sensor drift. It could be resulting from the turbine, the LiDAR device actually moving on the turbine slightly. But it does serve as a check to actually get towards our destination when the drone calibrations took place and increase confidence in the drone method dramatically. So some more plots here, and the top ones are the ones that you saw previously, and now we have 2 more at the bottom, one including the pitch and roll offsets and one including the motor drone offsets. And this actually makes an enormous difference in the resulting positioning of the beam, which matters when you're doing your correction back to hub height and the extent to which you're doing any extrapolation or interpolation. So this motion compensation coupled with the hard targeting from drones and turbines, key components to build robustness in the data. Lastly, I'll go through this one fairly quickly. We wanted to run WRF, weather research and forecasting model, with and without a wind farm parameterization, and calculate a spatial correction. This spatial correction method was done statistically by binning by direction for certain wind speed ranges, and only when the wind speed ratios relative to a given point in space that we selected were larger than any underlying numerical variability, which you do get from WRF. It doesn't have repeatability every single time because of randomization and seeding in the model itself. So only then would we apply a correction. But in the data that you see later on in these slides, I have not applied a spatial correction just for reference. Lastly, there's the time synchronization. At the time, we had two wind farms that actually came from two different legacy companies with two completely independent SCADA systems and IT infrastructure. And to get around that problem, we installed a line of sight antenna for the data transfer. So all the LiDAR devices are actually on the same common local area network. If an LTE solution had existed at the time, we definitely would have used that. So now I'll move on to the results section. Okay, so the GloBE measurement campaign took place between the September of 2021 and concluded in the May of 2022. You see a time series there. The grey is the from the ultrasonic measurements from the MetMast, and the floating LiDAR in position A is in dark blue, light blue is position B, and the turquoise is position C. There was a slight gap while the device went back to base for calibration and returned. But if we look at, just for the sake of context, what regressions can look like from other measurement technologies like anemometry or ultrasonics or traditional vertical profiling LiDARs, it's good to put into context what we get from GloBE. So here, just as a caveat, these MetMast data are completely raw and uncleaned. So there is going to be noise in there, there's going to be masked effects, and I'll point these out, but this is just, again, for a bit of context. And this is comparing the topmost anemometers on the stud-mounted booms on the MetMast between them as a regression. And we do see this tabular shadowing. Then comparing against the ultrasonic against each of these top-mounted anemometers, we do see a big masked effects there and the orange points from the expected wind direction. The color, by the way, is indicating what the wind direction is on that vertical color bar. Next, we have the profiling LiDAR, which was newly purchased for the sake of for the purposes of the GloBE project. And that is acting as a redundant and also reference source without any of these sort of masked effects in there. And you can see, compared to each of the topmost anemometers, the level of scatter we get in these regressions. And lastly, the floating LiDAR, which is co-located with the MetMast against the two topmost anemometers. And I do have to draw your attention to the fact that this is not representative of floating LiDAR performance, because none of the data from the MetMast are cleaned or anything. But it is indicating what sort of motion effects you can get from the floating LiDAR as an additional source of scatter. Also from the MetMast, we have a distribution of Manin-Oberkopf length, which is a characterization of your atmospheric stability. I've classified them, as you can see in the legends. And the left-hand side we have from the MetMast itself, and the right-hand side we have from WRF. And these data were calculated and provided by Fraunhofer Evis through the collaboration with Crosswigs. And you can see that on the right-hand side, the x-axis is month, and on the far right you have all. And the distribution between the model and the measured is actually very similar for this concurrent period. Now we have an additional factor here, which is what level of post-processing we did for the dual Doppler reconstruction before we get to any final plots that I can show you, which indicate a blockage effect. So first thing we need to do is filter out any extreme outliers. And to do this, in addition to the standard cleaning which TNO performed when creating the 10-minute dual Doppler averages using the standard filtering criteria for scanning LiDARs, this is an extra level on top, and I created a relationship between the MetMast and the 10-minute dual Doppler reconstructed points. And if the relationship was greater or less than a factor of 2, I considered this point to be unphysical, which you can see on the left-hand side, that's that ratio. And on the right-hand side, this has eliminated a good number of points which you believe to be physical outliers and not actually real measurements. Fortunately, for a very small cost in data. And all of these points are actually kind of upward, suggesting this is related slightly to the motion correction and maybe the extrapolation or interpolation. So how did we do overall? How did we do with this dual Doppler reconstruction? We had multiple methods which were new and novel, and we've gone to extra lengths to correct out any sort of bias. Here you see two scatter plots. The left-hand side is without this additional post-processing to remove outliers. The right-hand side is including it. And this is for pair 1, 2, where we have this nicely co-located point with a floating LiDAR. So in space, this is measuring the same point over the same time. We have a little legend on the right-hand side here, which is the level of correction which has been applied, what steps have been applied in this data set. So this is completely raw with no corrections whatsoever. And we get a very good R squared as a starting point. And the gradient is also pretty good. So there's no substantial gains suggesting there's an issue. And the test here is by introducing these correction steps, are we making things worse, about the same, or better? So as we introduce the motion correction, we see the points move slightly. As we move, and the gradient starts to improve, the line of sight correction moves things a little bit again. Introducing the offsets using the drone-based method moves things quite a bit. And we were using a linear interpolation method to reconstruct what the points should be at the height we wanted above sea level, which is 90 meters. And then we used a power law using an assumed value of shear of 0.09, which had very little effects overall. When we go to wind direction, we also gain a lot of confidence here in the measurements from the LiDAR. I'll step through all of the correction steps. That's including motion correction. That's including line of sight. That's including drone. That's a switch to the power law. And we see that actually one of the biggest impacts here on the regressions is the removal of the outliers. If we then change this target point, keeping the floating LiDAR in the same location, but then using this point over here, what would we expect to see? We would expect to see an increase in the level of scatter in these regression plots, indicative of a spatial effect, so an uncertainty. And that is something we entirely expect over a 4 kilometer distance, or approximately a 4 to 5 kilometer distance. Okay, so now we get into these key transects and how have we actually done with respect to the KPIs that indicate a blockage effect, and what do we expect to see? In these plots, this is x-axis is easting, and the y-axis is a wind speed ratio relative to a point which is indicated on the plots as the normalization point. This is without any sort of motion correction, and we have 270 degrees plus minus 22.5, that's a 45-degree bin. That's to try and capture quite a bit of data. We would not expect any sort of acceleration because we are going to be capturing some level of wake in the Kaskasi gap with a direction bin this wide. And we see there's quite a lot of noise here. Once we introduce the motion correction, we still have quite a bit of noise. Once we introduce the line of sight correction, that also changes things quite a bit, principally because the line of sight corrections were applied to GloBE LiDARs 1 and 2, which correspond to the dark blue pair here. So any substantial changes in those points will reflect in all of the wind speed ratios. Once we then apply the drone-based offsets, then that has a substantial effect. And this is essentially the end of the correction steps that were applied to these data. And this is tending towards now our final data set. And what do we see? We see these characteristic blockage-induced upstream decelerations. As we move closer to the wind farm, we get a deceleration occurring. We also see this emergent downstream wake effect where the wind speed is lower or subtly lower than the upstream points due to the wakes in over the wind direction bin range, because just an aggregate starting to impart themselves on these measurement locations. So what actually looks like very, very small changes in these regressions relative to the floating LiDAR with each correction step translates into quite a big effect when we're trying to look at blockage. And this was a big success for GloBE because we were able to we had known sources of bias, and we were able to, we believe, back out most of the impacts of these known sources of bias. If we refine the wind direction range down to 270 degrees plus and minus 5, degrees. That's only a 10-degree bin now. We don't expect any wake effect to appear in these data in the downstream. We then get this nice sine wave style shape emerging of a characteristic deceleration as we saw before, but also a blockage-induced acceleration downstream. And the inset plot here you see is from our VV model, where we have a deceleration appearing here, then relatively speaking, an acceleration which goes above unity. And we'll be able to dissect what unity is in the next section using the models to help us indicate what that is. But we do get then this characteristic acceleration. So that was, again, quite a big success to see that emerge. I have an animation here now, which is showing you all the wind sectors, well, not all the wind sectors, limited range, but much expanded range of wind sectors, starting off from the east and southeast. We have not only the wind measurements normalized to the same point in the previous plots, and these are animations which will show the plots that I've just shown you, but for all sectors, again, all relative to this point, but also the wind farm production data. So blue points are less productive turbines, red points are more productive. And from this wind sector, we're seeing a wake on Nordsjøst here from mere winds, so less productive turbines here. And this is a pattern of production. So a pattern of wind speed and a pattern of production on the same plot. And if I initiate the plots, we start here and we move around towards 180 degrees. And then as we come around to 180 degrees, you see that we get a nice symmetrical U shape of wind speed as the wind speed tends towards unity or a bit of acceleration around. Then we get a wind farm wake impinging on these points downstream, which is what we see here. We see these deceleration points here. And then as we come further around, we get a wake moving across from Nordsjøst on Amrum Bank, and we tend towards these wind sectors that, or we get an acceleration at 10 degrees. And then we go a bit above unity there, and then we come back around and start getting another wake imparting itself on the downstream points. So this is quite a nice way to see as a sanity check that firstly, where it's windy is where you would expect it to be windy, and where there's power, we would expect there to be power, and it all tying up into one common story. Another nice little test that I did was to bin the wind speed, the KPI, so the wind speed ratio, as a function of wind speed itself. And why does this matter? It matters because at the low wind speed region, between 4 and 11 or 12 meters per second, we are at the high thrust part of the thrust curve. And after that, we are emerging into the rated power where then thrust starts to reduce substantially. And in terms of AEP assessments, we get the maximum effect of any turbine interaction blockage or wake at the max thrust region, but we'd also expect that blockage effect to diminish as a consequence of the wind farm thrust overall tending towards zero as a function of the thrust curve. And that's something we do see materialize, which is also reassuring. So this reduction in the farm thrust is leading to a reduction in the blockage effects as a nice sanity check. I'm going to go through these points here very quickly, just keeping an eye on time. So if we look from a wind sector from, I think it's 300 degrees, 300 degrees with a 30-degree bin, and look at the production data. We also have all of these turbines with real operational data with a power output, so we can establish what this pattern of production is. And if blockage was not to exist, we could hypothesize that the lead row production, which in this case would be these turbines and these turbines on Amrum Bank, would all be at its maximum, all be the same. However, that's not what we see. We see non-uniform spread of power. This is a much longer data set, a 3-year period, rather than just the GloBE period, to get as much statistical significance as we can. And then I used the WRF data, which has boundary layer height in it for the same concurrent period to filter out low and high boundary layer heights. So this is between 0 and 400 meter boundary layer heights, so very low. And we see quite a strong relationship of non-uniform production, with turbines becoming more productive as we go further to the east. As we filter for the higher boundary layer height range, the strength of that relationship then decreases. Of course, when you're filtering for low boundary layer heights, that is a proxy for stable atmospheric conditions in which larger wake effects would manifest. But nevertheless, if we focus on these points here, and we've normalized by this point in the corner, this turbine in the corner, and we plot this as a function of boundary layer height, we see that as we increase the boundary layer height, the ratio of power tends to decrease. And that is indicative of a secondary effect of the atmospheric conditions on blockage. And we see here as well the distribution of the boundary layer heights, which I've used to filter by. We did actually take a measurement of boundary layer heights within GloBE. And we have here a box plot, which is showing you the distributions, so the medians and the overall width of the distribution from error 5 over a 20-year long term, error 5 over a concurrent period, WRF over a concurrent period, and the derived from measurements as well from GloBE. And we see that the distribution is first of all tighter, and that on average the boundary layer height is lower. There is a lot to unpack when understanding how boundary layer height is computed from each model's data source and in the measurements. However, on the surface, we do get a lower on average boundary layer height coming from the measurements. And we see the time series here as well from the measurements, showing there's reasonably good agreement in terms of phase between the measurements and the model. So now we reach the conclusions part of the presentation. So has GloBE actually achieved its goals overall? I would say yes. So we've successfully executed, I say probably, the largest single measurement campaign offshore, and certainly one of the most complex ever run offshore. We've implemented a set of complex and comprehensive corrections to remove known sources of bias that we identified upfront. And we've controlled for those as best as we can. And the reason for doing that is such that we can give you, the industry, the most robust data set that we possibly can within the current technological limits. We use new and novel techniques to ensure that we were left with a statistically meaningful blockage observation that we could then start to compare models to and create some definitions and understanding as to what the blockage is, how to model it, and how to account for it. And we combined wind and turbine operational data, this pattern of wind speed and pattern of production. We've brought them together such that we can enable this delineation of the blockage effect. And it's also worth noting that the measurements alone are not enough to describe the impacts of the blockage. That has to propagate through into the modeling space as well. And actually, the models are crucial to unpacking what particular physical phenomenon are under the hood and going on behind the scenes. But that's for the next webinar session. And I would also like to, in case you weren't able to attend Wind Europe, there is a GloBE dashboard, which is currently online. You can access it through your phone with a QR code, or you can access it using the login details and URL below. And that is a dashboard where you can interrogate the data that I've presented here for the GloBE period and replicate the plots that I've shown. There's a couple of bugs that we're working through relating to the SCADA data, and a quick update that's coming very, very soon as well to furnish the links on the dashboard. However, you are very welcome to have a play. Leave it there in case there are anybody still getting the links. And finally, linking into the next session, we have this independent technical review group. And the purpose of that is to get a body of organizations and research institutes, etc., from across the industry to all come together and use the GloBE data, the learnings, the outcomes to form an agreement and a consensus on what blockage actually means. So first of all, we have the GloBE data as a part of that, as the foundation. Then we need to add in the blockage physics and model representations and how to separate all of that. And then the how to treat blockage as a technical loss and an accountancy exercise in the losses sheets for any AEP assessments. And the outcome of all of this is a joint statement on the global blockage effects, which we will draw your attention to the next time and go through in more detail. But that is something that's already been published and people made aware during Wind Europe Technology Workshop. So that concludes the technical part on the measurements. There's an awful lot that I wasn't able to present today, only through lack of time. During the whole project, we generated more than 3,500 slides of material, which I would love to bore you all with, but we only have an hour, unfortunately. But I would like to draw attention to, firstly, my colleagues who put in a huge shift and big effort to assist GloBE all the way through to its conclusion. It was a big joint effort. This is just in the resource assessment and methods and tools departments within engineering. And also draw attention, so some special acknowledgements to these individuals from DTU, Fraunhofer, and TNO, who without these people, the project would not have happened, and a serious amount of brain power from this group to make GloBE work. So thank you again to them. And finally, it was made possible through the Carbon Trust and as a consortium of all the organisations and public funding bodies that you see here. So an extra thank you to them as well.
And most importantly, thank you, Chris. There's a huge amount of effort has gone into this, and I think it's made a real difference to the industry. So thank you very much to you and your colleagues for all the efforts on this. We do have 10 minutes left for questions. I'd again encourage everyone to put questions in into the Q&A function on Zoom if you can. We have a couple in already. So the first one is actually a three-part question, maybe some of which I can field and some of which Chris can field. So first of all, is there a follow-up project planned? Can new partners be involved? And have you considered measuring wind speeds at hub height using other technologies such as spinner anemometers? Is there a follow-up project planned? Not immediately. We know there are some unanswered questions at the end of GloBE. There's always more we can do. I think Chris will touch on that in a bit more detail on Thursday. So we're certainly open to the idea of doing more projects on this in future. And if we do, then yes, absolutely, we would welcome other partners to get involved. Regarding the measurement technologies, Chris, feel free to jump in on this, but there was a huge amount of effort put in to determine the most robust way of teasing out these really rather subtle effects. And for this purpose, scanning LiDARs as the primary measurement tool made a lot of sense. Do you want to comment at all on the use of spinner anemometers in future?
Yeah, so just to add to that, we did consider all of the currently available technologies for the purposes of GloBE. Even putting a floating LiDAR at each of the points that we had proposed in order to get these wind speed gradients, that would be an extremely robust data set, however prohibitively expensive, because floating LiDAR technologies are not exactly cheap. So we had to strike a balance between what could work within the budgetary constraints of the project, what devices gave us flexibility, because the scanning LiDARs give you an awful lot of flexibility, and also how we could best use those. As I mentioned previously, we thought that actually doing a continuous scan would not yield the uncertainty that we required to meet the objectives of GloBE. And regarding spinners, once you get to any sort of turbine nacelle mounted measurement technology for monitoring upstream wind speed for turbines doesn't measure far enough upstream. You are dominated by local induction zone at that point for that turbine. The blockage effect is known by many names, and wind farm induction is one of them. So we needed to extend beyond what is a local blockage effect, turbine induction, into a global wind farm induction region. So that prohibited the use of the cell-based technologies.
Thank you. Second question then, you talked about the stability measurements on site, and you talked about the sensitivity of the blockage effect to atmospheric boundary layer height, and you sort of mentioned briefly that those two things are correlated. Can you expand a bit on how you sort of tease out the separate effects of those two things, and also whether there's any seasonal bias introduced by the fact that the campaign run from September to May?
Yes, so I'll deal with the last one first. The seasonal bias is something that we did actually have quite a bit of concern about. However, something slightly unintuitive happens during our investigations as to when to run the measurement campaign. We weren't exactly rich in options as to when we could run it. We had a time constraint of when the Kaskasi wind farm's first turbine started spinning, so it needed to complete before that point. But actually for the boundary layer height seasonal bias, we saw the highest boundary layer heights in the summer, in the winter periods, and the lowest then starting to emerge in the spring. So we did actually have a shorter measurement campaign planned Fortunately, we were able to get on board some more partners in that time, and that allowed us to extend the measurement campaign on 2 occasions to cover our time up into the spring. So actually what we covered was not a single season, but the transition between 2 as a function of boundary layer height. The second point, or the one before that, about the link between boundary layer height and atmospheric stability, it's a hard one. It is a hard link. The boundary layer height is as a function of your atmospheric stability. You can't separate the 2, which is why you would get a stable conditions and more persistent wake, more pencil style wake for lower boundary layer heights, and vice versa. So we can't decouple those. And when we're considering how to model a blockage effect, this is blending into a topic for next time, it becomes a very difficult parameterization problem, because you can't independently change your boundary layer height as an input from your turbulence intensity and from heat flux or anything else. So that it becomes quite a difficult problem to solve from a modeling perspective. But you're absolutely right that you can't separate truly the effect of boundary layer height from others, because there is a seasonal effect, there's a diurnal effect, less so offshore. It's all completely connected.
Thank you, Chris. I think we've got time for one final question, which is very much just a measurement related one this time, I'm glad to say. You mentioned reset and backlash points and the way that the LiDARs were set up. Can you expand on that and explain what those are, please?
Sure. So the backlash is, and the technology is actually advanced using belt drives now to get around this issue. However, the devices we had available at the time used gears in the head to actuate the head and to move it. And the gears have a tolerance, which means that, strictly speaking, if you start at one azimuth, go to another azimuth, and come back again, you don't end up exactly at your starting azimuth because of those tolerances. So to combat that, you can address that in the actual measurements themselves by setting in a backlash dummy point. So instead of going up a set of points, then to the next ones, and then down, and then up, in which case you would introduce that backlash issue, you reset back to the bottom and get the gears engaged to go upwards, and then introduce this dummy point just for a moment, and then step through your actual measurement points to try and mitigate the backlashing effect, or at least minimize it as much as possible.
Fantastic. Thanks so much, Chris. We are pretty much out of time, I'm sorry to say. I just wanted to say again, thank you very much to Chris and all your colleagues. Thank you very much to everyone who's been involved in the project. And thank you to everyone who joined us today. It's great to have a good turnout on the call. And we hope to see you all again at the same time on Thursday afternoon when we talk through the modelling and accountancy aspects of this project. We will see you then. Thanks all. Bye.